Okay, hello everybody. We're the last presentation before lunch, so I hope you find it interesting. I'm John Mangan from Intel, and
yeah, I'm Steve from Intel.
Okay, so our presentation is called Fine-Grained Device Sharing. And if I can find the button here. Green button. There we go. So what are we going to actually talk about? So Steve's going to describe a bit in detail on what resource sharing is all about, resource slicing. He'll describe the requirements, the motivations, and why this is important for cloud-ready and cloud-native environments. Then Steve will go into some more detail on how he's taken advantage of a mediated device framework, and in particular enhancing DPDK to be able to expose and consume resource slices in a consistent manner, a standardized way. And then I'll walk you through an example of device slicing that we've implemented using an Intel FPGA programmable acceleration card. Okay, I'll hand you over to Steve for the first pieces.
Yeah, thank you, John. Yeah, so we are talking about advanced resource slicing. So network slicing is a very end-to-end point of view, but our focus talk today is about device-level partition. So here's the state of art is that we run DPDK and there's affinity on dedicated cores and running there. And on the device perspective that we have to import PMD on top of the device. So the device is presented by bus device function. Here's the situation. And each of the devices actually have a few queue pairs associated with it, which is today most of the case is a fixed mapping. So, but in another side is that, so not every application or workload are always running. So they might run for a while and then switch it to another. So there's a very critical number is how fast you can switch from one to another, right? So we know that actually the number, if we're looking at the numbers, so there's like hundreds of thousands of the isolated instance is ready to be run on a process. And it is very lightweight to schedule your workload from one core or running there. But the hard piece is that on the device perspective today is very fixed. There's a few gaps if we look at it. So there's thousands of the isolation or hundreds of the isolation instance. But on device, the number of the device, the VDEV represented by VF are hundreds. So that maximum number is 256, right? So there's a gap between them. And another side is that device is not so, the resource in the device is not so dynamically. You can dynamically allocate a piece of the queue pairs and associate it with one VDEV. And so we see the gap there are hundreds of the VDEV and thousands of the instances you are going to run. So, and also for each of the running instance, there need to be address space isolated from each of the other. And so the gaps there is that, so what if that to support thousands of the isolated instance with the hundreds of VDEV? We have two ways, right? So the first way is that we can extend the VDEV, so that's the scale outweighs. Another is that can we like provision the things? So one VDEV, because even the thousands of the instance, they can run in the same time because of the core count, right? You always need to over provision that. So can we do that over provision on top of the existing number of VDEVs? So, and another is if the hardware support to locate the queue pair, can we dynamically map to the PDF and expose to the application? So here's the things is the things is introducing our virtual device. So keep the device have a minimal set of the partition states and have the states being maintained and in our virtual device. So here's the advantage we can see. So So first is on the scalability perspective, it's going to need to address the like thousands of the isolated instances, how can address that. And on the device resource perspective, how we can support user-defined granularity, and how that even you have limited device numbers, that how can provision that. So, and that under consumer's perspective, the workload, is that necessary to care of all the functions the hardware device provided, or it's just enough that have a like portion of some of the surface access to the device? And keep that subset of the function which is compatible from one generation to another. So that's the beauty of the introducing some interface like intermediate device and put the control states there. So here's the notion. So from today that we have the device pass-through. So basically you have the device control and device the configuration are all exposed directly by the hardware. So your driver, whatever running the bare metal process or VM, you are very aware of what the hardware really gives you. And also you have data plan direct I/O provided by hardware device, and they're talking directly to the PMD. So there's another side is, what about that your workload consume the device, which surface is defined by software? So basically the virtual device provider surface that you configure, whatever you configure is actually defined and provided by software. So the minimal set provided by hardware is about just a data plan to provide a direct I/O, and also helps you to co-work with the address-based isolation. So there are two parts to make that happen. The first part is on a software level. So in kernel also it introduced a mediated device which can expose portion of the device resource as a device under application perspective. So, and the surface is defined actually by the software. So, and in the VMM level, actually you still have a physical device driver there, but always running on the host. It's not necessary to provide the real function configuration to the guest, but you just helps to maintain the functions on the host side. And then another side is for partition, right? So you device do the I/O directly to the guest memory, to the workload, the memory provided by workload. So there's a few ways to provide a different granularity isolation. So we all know that single DPDK today is already being used for everywhere almost. There's a coarse granularity. For smaller granularity, either that you can, some of the device provided translation from the virtual address to the physical address, that's a device specific. And also that actually Intel published a spec for the scalability, which provide a smaller granularity on the platform side. And also have spec published for the VDEV to do the enhancement to support, like adding the passage together with the VDEV to provide the address separation. And then that is cool, right? And what about on the DPDK side? Are we get ready to support this kind of device mode? So if we're looking at the usage, so once kernel provides this media device, and the device will support that. So if we check on the virtualization side, it works well. So kernel actually exposed the media device, nothing different than the PCIe device. They provide like by the VFIO APIs, right? And you can generate any media device instance and assign to Cunming, and the Cunming took over it and run as a VFIO device and expose and emulate the PCIe bus to the guest. That just works. And but what about running like bare metal or DPDK in a container, right? So DPDK supports VFIO well, but that is like VFIO for PCIe. But for MDEV, it is not the same things because MDEV is not represented for any physical bus. Actually, so a lot of physical bus can be exposed by MDEV in different device API. So that is the gaps today. So we need to get that native support on DPDK side. So here's the situation. So look at device A, that's our user device, which is on top, the physical bus, PCIe physical bus, and we expose by VFIO PCI. And in DPDK, we have a PCIe bus, so you have a driver can probe the device and get its run. And then the device, another device B actually is in the same function. And right now we put it in the MDEV framework, what happens? So basically you have a driver, right? We call it a parent device driver. Why call it parent? Because it will register and generate our MDEV, media device. And the media device will expose to the user space by VFIO. Then what is about the bus? First of all, this is not a PCI bus, this is the media device bus. And then, so this is our device just to expose portion of the resource. That means that you have to use the different PMD for that. Actually, if that type X device, you already have that in DPDK, why not just use that, right? So then, how for existing like PCI device driver to drive that media device? And then the second question is that for one device, you expose cube here, but not necessarily you expose the same surface for the configuration for your end user, right? You may provide different functions defined by yourself. So where is these driver put in? That's associated with the existing like PCIe driver list or what else? Here's the function we need to address. So here's the way. So for media device perspective, right now it not support like the support your device have a physical isolation on MMU side. So in the kernel community, there's an effort to enable like media device support your device can use MMU and also add extension for the scalable V support. And on user space, if we're looking at DPDK, okay, media device is exposed in sys bus, right? This is a media device bus. And then here's the way. So DPDK is well defined on the structure on the bus device driver, right? So we can introduce a new bus, which is media device bus. And that is either you can scan as normal and scan your device, probe your driver. And what is the driver? So here's the, when you scan the sysfs, then you find the device, and you add it in the new media device bus. And then we provide a driver. The driver is the driver will identify the device API, which is sysfs provided by media device. Once we find, okay, the surface under the media device actually is a PCI, then this driver, this bus driver, which we call the VFIO PCI driver, will generate a device instance back to the PCI bus, so that your normal existing PMD can probe that device as usual. So that's the way we keep that your existing PMD still works on that portion of the resource, which is wrapped by your media device. That's the way we do. So, and there's a few other interesting things is that, so if we're looking at the interface layer, so for no matter the VM and the native DPDK, we are consistent on the device interface with talking with kernel. That's VFIO, because media device is nothing new in terms of the API level. They are all general VFIO API, nothing changed. So all the things PCIe or other bus or media device are all hide by this interface. That's a good device abstraction interface. Then underneath is that you can do a few interesting things. First things is that media device, which is always being part of kernel. Today you can't provide any software or any device or a media device in user space. What about that in user space, you provide that virtual device, provide that media device in user space. That is one area we are investigating. Another is that there is acceleration for the VDIO, which is called a VDPA. So VDPA today also on the kernel path, it exposes the vhost backend by a media device. So the interface also can expose by this way to provide a good device partition, even for the, what I call is over provisioning, right? Even the number of VF is limited, but you can still over provisioning because the device states is saved in the media device and can be restored back. And the last piece is that for some of the device which is memory-based, it's very up to the user how to partition their memory into page boundary and map it to your application. That's so here is the example like using NTB, which is basically it's a memory-based, so you can partition anyway and expose there. Yeah. Then John will talk how to build a fine-grained device from scratch.
Yeah, so I'm going to describe a kind of a real example on how we've implemented device lighting in a prototype implementation. So as a device basis, what we've used is what we call the Intel PAC card. So this is a family of FPGA cards that Intel have commercialized for consumption in servers and data centers. So it comes with its own framework. You can see kind of on the right. So the actual FPGA part itself has two pieces. There's a piece called the accelerator function unit. So that's the image that the user does that represents the actual accelerated function that they want to put in place. This can be RTL-based or OpenCL-based or whatever tool is used to create that bit stream. However, it doesn't have to worry about the whole interfacing then in the server environment. What's provided with it is the blue bit stream which we see alongside it, which is effectively the plumbing. So this abstracts the AFU from the PCIe bus and provides facilities for dynamically loading that bit stream, for configuring it, for exposing regions and that type of thing. And then on top of that, in the actual server itself, there's a series of layers. There's a few drivers. One is a driver for the actual accelerator function unit itself. This is a generic driver, so this isn't specific to the use case of that green bit stream. And then we have some management drivers that actually orchestrate the loading of the bit stream, the pulling out of stats on what's going on, the IDs of the bit stream, that type of thing. And then on top of that, there's a user space library that the actual user can call, and effectively that exposes the kind of the raw interface into that green bit stream that the application can write to. And that framework is called the OPAE, Open Programmable Acceleration Engine. That's upstreamed in its own right in 01.org and works just fine. And then the whole environment can be put together. There's a simulator where you can write the user application and the green bit stream and simulate the thing together and build your overall use case. So it's just to kind of facilitate the development cycle of these kind of FPGAs in server environments. So that's what we're using as the basis for this device slicing. So the typical use of this today, if we want to expose it to DPDK, that AFU is effectively a complete unit. So the full unit gets absorbed by DPDK. And then if we write a BMD within DPDK, and we have some examples of this in prototypes where effectively we write to that OPAE API, and it allows us to get access to the full 256K MMIO region in that green bit stream, and also to map user space buffers so that the FPGA can read and write into the DPDK memory as well. So you can build a single application on top of that, and that works just fine. But what if we want to share that AFU, that accelerator function unit, and expose it to multiple VMs or containers? Have a piece of acceleration for one VM, or possibly have shared accelerators, but not look at it as a single block and effectively implement the resource sharing that Steve has been presenting here. So what we'd like to be able to do is, instead of having this as one complete block, we'd like to be able to map that AFU into multiple virtual spaces. So effectively, we'd like to be able to divide that MMIO region into blocks and expose just a piece of it to a particular virtual address space. And similarly, we'd like to be able to map buffers from virtual address spaces to that FPGA in a secure manner and in a kind of a unit by unit way. How do we do this? What are the steps to actually get this scenario implemented based on the MDEV and the DPDK enhancements? So what we've done is a couple of steps. And just to bear in mind, the only thing we've actually modified here is our own AFU driver, so the driver that specific to the FPGA. All the other pieces are generic and part of the MDEV and DPDK. So effectively, we start by telling that AFU driver, what's the configuration of that AFU, how many slices there are in it, if they're the same, if they're different, what's the pieces of MMIO we want to map, etc. And then we trigger a registration with MDEV. So the MDEV driver is registered through AFU, and that creates entries in the CIFSS of the MDEV of the different types of devices there and what they're capable of. Then the second step is to create instances of that MDEV that can be consumed. And then thirdly, we bind the VFIO to those instances and effectively have a means of exposing the different parts of that FPGA AFU device to different applications. So there are the steps to getting there. And then effectively, what do we have in the end? So now we have the AFU at the bottom with its different spaces. There's a range of VFIO devices exposed. And then DPDK, whether it's in a VM, and the VFIO devices are brought through with QEMU and exposed as an emulated bus in DPDK, or using the MDEV extensions in DPDK from bare metal or a container. We can have multiple DPDK instances sharing that AFU device. And that could be for individual acceleration functions like an inference engine or a DPI or something like that per application. Or there could be shared, so that could provide a communication path between two DPDK instances, be it for switching, be it for passing metadata, be it for shared atomics or whatever. So that's pretty nice. And the one thing bear in mind on this implementation, so we only have a single BDF on that AFU, so basically one IOMMU group. So we have the host that actually does the programming of base addresses to the FPGA, and the actual applications themselves use offsets. That way we ensure the security and the boundaries between the different VMs to the actual memory, and that there's no kind of cross security issues between them. Okay, so yeah, to summarize, I mean, we have a set of requirements around scalability, provisioning, and resource composability. That's driving a need for resource slicing. We've shown how by leveraging MDEV and enhancing DPDK, we can expose and consume those slices in a ubiquitous manner. And then there's we've shown a couple of use cases and described one on how actually this can be done. And what's nice is that that device can be a real hardware device, or it can be an emulated device or a software backend, so the actual application doesn't know where that slice is actually sourced from, be it hardware or software. Okay, thanks very much, and I guess we'll open for any questions. Or everyone wants to go to lunch. Sure, work away, yeah.
The idea is to have hundreds or thousands of applications using the device, right?
Correct. So the applications can access a device, in this case, be it a hardware or software device, yeah. And
so one of the problems that could happen is the IOMMU overhead. So you have to do IOMMU mapping for hundreds of thousands of different independent processes. And have you tested this? Because with current DPDK, the way we use heap pages, that is good for IOMMU mapping for the IO TLB pressure. But I guess if you have hundreds or thousands of different applications using IOMMU,
so we do leverage the IOMMU to write directly into the guest memory space. However, the mapping is controlled at the host level. So,
but the DMA addresses are given by the application.
So the way in the FPGA, the DMA addresses are given by the application, but they go through an emulated region in the host. So The application gives a base address, and the host uses that to do the mapping into physical memory. And then the actual descriptors or usage of that memory from the application is done using offsets in this particular case. Now, if we've got multiple VFs, we can separate them, and in the future, we're going to have passage to allow more groups on that IOMU. But in this particular sharing case, we have the host that actually does the physical address to avoid one guest being able to provide an address that writes into another one. Yeah.
Thank you.
You're welcome.
Okay, I
Okey
guess
doke.
that's it.
Thanks very much,
guys.
everybody.